Hello, this is Dr. Hanaa Assil, and this is Unit 4 of October 2023. So this is October-November 2023 in the Pearson Edexcel International A-Level. So let us take a look at the questions and discuss the answers. So the first question says, which method would be most suitable to investigate the kinetics of the reactions shown? So if I have this reaction, how can I determine its rate? Of course, one of the methods is colorimetry, but can I use this? Colorimetry is used if we have some change in color. We don't have any colored substances here, so you cannot use colorimetry. Measurement of change in volume, well, this is a gas, so yes, you can use measurement of change in volume. Let's check the other possibilities. Measurement of change in mass, we cannot measure mass for gases. Quenching with ice cold water followed by titrating with acid. We use this method if we're using a base, sodium hydroxide, in the reaction, for example. So for example, this equation where we have sodium hydroxide reacting, how can we measure the rate? Yes, we can measure by quenching with ice cold water followed by titrating with acid. The equation for the reaction of bromate ions with bromide ions in acid solution is shown. The rate equation is this. The concentrations of all reactants are doubled. Notice that the rate equation indicates that this equation is first order with respect to bromate, first order with respect to bromide, and second order with respect to the H+. So if we double the concentrations of all the reactants, by what factor does the rate increase? Of course, when you double it, that means 2 to the power 1 times 2 to the power 1 times 2 to the power 2. So the total of that, you're going to increase the rate by a factor of 16. This question is about rates of chemical reactions. Which graph shows a reaction that is zero order with respect to reactant Q? So we have two types of the graphs in front of us. Either concentration of Q versus time, or rate versus the concentration of Q. Now, which of these shows a zero order? Remember, zero order means as we change the concentration of Q, there is no effect on the rate. So B and D are wrong. For a zero order, changing in the concentration of Q would have no effect on the rate. It would not increase it and it would not decrease it. So B and D is wrong. So we're choosing between A and C. Well, if it is zero order, that means with time, the concentration is decreasing, it's being used up, but there is no effect on the rate. So remember, these graphs that we should know that if we're talking about rate versus concentration, a zero order would give this kind of graph. First order will give this, a second order would be this. So this is rate versus concentration. What if we're talking about concentration of the reactant with time? If it's zero order, the concentration of the reactant decreases. With a first order, it decreases in this way, and for a second order, it decreases in this way. So keep all of these graphs in mind when answering the questions. Okay, the next question says the equation for a gas phase is shown. The reaction is first order. When the initial pressure of A is 2 atm, the half-life of the reaction is 20. What is the half-life of the reaction when the initial pressure of A is 4 atm? Remember, if we're talking about a first order reaction, the half-life is constant. So for a first order reaction, the half-life is constant. So if we have this graph of concentration versus time, Then half-life, you remember that half-life means the time taken for half the concentration to be used up. So if we're starting, for example, in that second graph on the right, from point 2 to point 1, the time taken for that is the first half-life. And then from the point 10 to point 05, the time taken for that is the half-life. So for a first order, the half-life is constant, while for a zero order, the half-life decreases with decreasing concentration. For a second order, the half-life increases with decreasing concentration. So this is a first order reaction. Remember that the half-life is constant, and it is constant whether the pressure is 2 atm or 4 atm. So the half-life is 20 seconds. The graph shown can be used to obtain a value for the activation energy of a reaction. So here we have a graph of natural log of the rate constant versus 1 over t. So from the Arrhenius equation that we have, you should know that if I plot ln k versus t, then the gradient is minus a over r, and that means that activation energy is the minus gradient times r. The energy cycle for dissolving calcium chloride in water is shown. The enthalpy change of hydration of calcium is minus 1650. What is the enthalpy change of hydration of chloride? First of all, what do we mean by enthalpy change of hydration? You should know that enthalpy change of hydration is the enthalpy change when 1 mole of gaseous ions dissolve in sufficient water to give an infinitely dilute solution. So I have gaseous calcium ions, gaseous chloride ions. I dissolve them in sufficient water to give a solution. So where in this graph is delta H of hydration? It's that long arrow coming down. So basically we're trying to use that to get the delta H of hydration of chloride ions. So all that arrow going down, so from calcium gas, chloride gas, to give calcium ions aqueous, chloride aqueous, the delta H of hydration is the total of the numbers that are given on the other side, the lattice energy and the delta H of solution. So we add them up, that is the delta H of hydration. Now he wants the delta H of the chloride ions. Remember that he's given me the calcium, so I need to subtract this calcium from the delta H of hydration. But remember that this is for 2 chloride ions. The value that I have is for 2 chloride ions. I want it for 1 chloride, so I have to divide by 2. So this is the delta H of hydration of 1 chloride ion. Why is the enthalpy change of hydration for magnesium ions more exothermic than that for calcium? So why is delta H of hydration for the magnesium ions a higher value than calcium? Remember, magnesium with respect to calcium. The magnesium ions have smaller radius, so this means they have higher charge density, and something that has higher charge density would dissolve more easily and have a higher delta H of hydration. So which of these choices is correct? The magnesium ions have a higher charge density, and that is why they will dissolve more easily, so they will have higher delta H of hydration. Okay, question 6 says heating copper nitrate results in the equilibrium shown. Which is the expression for Kp? Remember, how do we write the expression for Kp? Kp is the partial pressure of products divided by partial pressure of reactants. But remember, we do not include solids in equilibrium constants, Kp or Kc. We do not put solids, so it's as if they're not there. So the Kp is just the partial pressure of the NO2 to the power 4 times the partial pressure of the O2 to the power 1. Remember, it is the partial pressure to the power of the coefficient. Do not include solids in the equation. When concentrated hydrochloric acid is added to methanoic acid and an acid-base reaction occurs, what are the Bronsted-Lowry acid-base conjugate pairs in this equilibrium? Remember, going forward, there is an acid and a conjugate base. Going backward, there is an acid and a conjugate base. So if we're going forward, which one gave up its H+? The one that donated its H+ is the acid. So going forward, of course, is the HCl is the proton donor. So the HCl is the acid. Then the Cl- is the conjugate base. Then going back, which one gave up a proton, or which one is the proton donor? It is the HCOOH2 plus changing into HCOOH. So these are the acid and conjugate base. Question 8 says, at 100 degrees Celsius, pure water has a pH of 6, but at 25, it has a pH of 7. So, if we're talking about the dissociation of water into H+ and OH-, the question says at higher temperature, it is a lower pH. That means at higher temperature, I have more H+ ions in solution. And that means at higher temperature, this reaction goes forward. So what does that tell you? If I increase temperature and it goes forward, that means the forward is exo or endo. Increasing temperature goes endo. So if it's going forward, making more H+, so pH decreases, then that means that the dissociation of water is endothermic. So concentration of hydrogen ions is higher at 100 than at lower temperature. Question 9. 4 beakers each contain equal volumes of 4 solutions. The pH of the 4 solutions was measured. Which of the following gives the order of decreasing pH? Decreasing pH means I start with the one that has higher pH and go down. So, which one will have higher pH? The one that is more basic, or the one that has more concentration of OH- ions? So, which of these is more basic? Of course, beaker 4 has 0.1 mole per decimeter cubed. So, remember that beaker 3 and beaker 4 will be more basic than 1 and 2. Higher concentrations of base. And then between beaker 3 and 4, each mole of barium hydroxide has actually 2 moles of hydroxide ions. So beaker 4 will have more hydroxide ions. That means higher pH. And then beaker 3. Now comparing 1 and 2, remember sodium hydroxide is a stronger base, and that means higher pH, and then the ammonia will have the lowest of the 4 beakers. So that is the arrangement starting from beaker 4, beaker 3, beaker 1, and then beaker 2. This question is about the reaction scheme shown. Which reagent is required for reaction 1? Where is reaction 1? This is reaction 1. What is happening? And please note the direction of the arrow. We're changing acid, carboxylic acid, to alcohol. Carboxylic acid to alcohol means we're reducing the acid to give an alcohol. So which of these is a reducing agent that can be used? Remember to change acid to aldehyde, and then aldehyde to alcohol. We use lithium aluminium hydride in dry ether, or it could be referred to as lithium tetrahydroiodoaluminate, okay, or lithium aluminium hydride. Okay, Reaction 1 has a yield of 90%. Which one is reaction 1? That's the one we were talking about. It has a yield of 90%. What mass of 2-methyl propanoic acid, so what mass of reactant, is required to produce 6.66 grams of 2-methyl propane 1-ol? Keeping in mind that the 6.66 is only 90% of the possible yield. So that means we're given the mass of the alcohol. The first thing we need to do is number of moles of the alcohol. Number of moles is mass over molecular mass, and I am given the molecular mass so of the alcohol, that's 74. So this gives 0.09 mole. But keep in mind that the 0.09 mole is only 90% of the yield. So what is 100%? So if it is 90, it gives 0.09. So if it's 100, it should give how much? It should give 0.1 mole. So this is the number of moles that we should get if it were 100%. This is the number of moles of the alcohol. Now we're being asked about the acid. So what is the number of moles of acid from the reaction? It is the same number of moles. You can see that the equation says that the number of moles of acid is the same as the number of moles of the alcohol. So now I have number of moles of the acid, and we're being asked for what? The mass. How do I get mass? Mass is number of moles times molecular mass, and we're already given the molecular mass. So that gives mass of 8.8 grams. That means if I start with 8.8 grams and the reaction gives only 90% of its yield, it will give 6.66 grams of the alcohol. Which condition is essential for reaction 2? Which one is reaction 2? This is reaction 2. The acid changing into an acyl chloride or an acid chloride. And we're reacting the carboxylic acid with PCl5 to give an acyl chloride. Which of these is needed? Do we need an acid catalyst? No. We need an acid catalyst if we were doing esterification. If we were reacting the acid with alcohol, then we would need an acid catalyst. Do we need the reaction to be anhydrous? Yes. Remember that when you have the reaction with PCl5, we do not want water in the reaction. Because if we had water in the reaction, then it would react. And that is not good. So this condition for this reaction is that there should be no water. So it should be anhydrous. We don't need high temperature, and we don't need an ether solvent. Remember, the dry ether is used if, for example, I'm using the lithium aluminum hydride. If I were trying to reduce it, then I would need ether, but the PCl5 does not need ether. So remember, it needs to be in anhydrous conditions or no water. Reaction 3 and 4 produce the same ester. Where is 3 and 4? This is 3 and 4. It produces a certain ester, but by two different methods. So reaction 3 is the alcohol reacting with acid. Reaction 4 is the acyl chloride reacting with the alcohol. And the question is, which is an advantage of using reaction 4 instead of 3? Why is reaction 4 better? Remember that we said if we're trying to make an ester, it is better to make it from an acyl chloride than from an acid. Why? Because it can be carried out at room temperature. The acyl chloride is very reactive, and it will react at room temperature without a catalyst. And of course, the atom economy is not higher. It is based almost the same atom economy. And the hydrogen chloride is a product, but that has nothing to do with the fact that it is a better reaction. Which diagram shows two repeat units of the polymer formed by polymerization of these two compounds? So the first thing is I would draw what are these two compounds. Propane 1,3-diol. Benzene 1,4-dicarboxylic acid. So what is propane 1,3-diol? This is propane 1,3-diol. benzene 1,4-dicarboxylic acid, and we're trying to join them to form an ester. How do we join them to form an ester? Remember we said we remove the OH from the acid and the H from the alcohol. And also the other side we remove the OH from the acid, and the other side we remove the H from the alcohol, and we join. So this is called one repeat unit. So this is the unit that is repeated many times to form a polymer. Now what is the question asking for? It's asking for 2 repeat units, and that means this part that we have drawn, we need to draw it twice. So which of these shows the 2 repeat units for this polymerization? If you look at D, D is the correct answer. Do we understand that? Okay, question 12 says, polymer waste may be disposed of by incineration. Of course, the word incineration means by burning. At a plant carrying out this process with polypropene, a waste gas was produced that was thought to be either propane or carbon dioxide. These compounds have the same molecular ion peak in a low resolution mass spectrometer. If you calculate the MR of propane and carbon dioxide using the normal mass numbers in the periodic table, both of them will give 44. So in the low resolution mass spectrometer, there is no difference. But they can be separated at high resolution, because at high resolution we use the exact atomic mass that is shown in the table there. So what is the correct relative molecular masses of each one? Remember that propane is C3H8. So if I calculate the MR using the numbers in the table, then it comes out to 44.0632. What about carbon dioxide? It will come out to 43.98. So these are my results. Okay. Question 13 says, a thin layer chromatogram of a mixture of 2 compounds X and Y is shown. What is the RF value? Remember, thin layer chromatogram is a piece of glass that is covered with a layer of silica, and we use it just like paper chromatography. So we put the spots on the baseline and we put it into the mobile phase, which is the solvent going up, and they separate. So we have X and Y, and we're required to get the RF value of X. How do we get RF value of anything in the chromatogram? It is the distance traveled by the spot over the distance traveled by the solvent. Now, in the actual question paper, you can just use a ruler and measure from the baseline to X divided by from the baseline to the solvent front. But even without a ruler, just looking at it, you can see that X is below halfway through. So it is less than halfway through. So it's less than 0.5. Something less than about 0.5. So it is 0.38. It's not 0.33. 0.33, the spot will be lower than that. And 0.6 and 0.62, it will be higher than that. So the most reasonable of these choices is 0.38. If you're not sure, just use a ruler and get the answer. Y traveled further than X. So this is the chromatogram, and we found that Y went up further than X. How do the attractions between Y and X to the stationary and mobile phases compare? Remember, what makes something go up further than the other? If it goes up further than the other, then there is more attraction to the mobile phase, which is the solvent going up, than the attraction to the stationary phase, which is the silica on the thin layer chromatogram. So we're talking about Y, and we're saying if Y went up a lot, then the attraction between Y and the stationary phase must be less than the attraction to the mobile phase. So Y is weaker, the attraction between Y and the stationary phase is weaker than the attraction between X and the stationary phase. So that made Y go up. The attraction between Y and the mobile phase is stronger, so it went up more with the mobile phase than X. Question 14 says, this question is about the nucleophilic addition reaction between ethanol and hydrogen cyanide in the presence of potassium cyanide as a catalyst. The equation for the reaction is shown. Give the IUPAC name of the product. What is this product? This is the product that he got. How do we name this? Remember, the CN group is a cyanide group, or it forms a nitrile. So I'm going to choose that as the longest chain. How many carbons do I have in that chain? I have the carbon of the CH3, the carbon of the OH, and the carbon of the CN. So this is 3 carbons. So this is something propane nitrile. That's how we name it. And then I have a hydroxyl group on the second carbon. So this is 2-hydroxypropane nitrile. Complete the mechanism for this 2-step reaction, showing the structure of the intermediate, curly arrows, relevant lone pairs, and dipoles. So if we have the cyanide group with a negative charge, what is the first step that happens? You should realize that the cyanide group is a nucleophile, and that means it has a lone pair of electrons. If I have on the C triple bond N, I have a negative on the carbon, that means there is a lone pair of electrons. So please bring the arrow from the lone pair of electrons on the cyanide, not from the negative charge. Lone pair of electrons on the cyanide will attack what? If I have a carbonyl C double bond O, then the carbon is slightly positive, the oxygen is slightly negative. So the lone pair of electrons on the cyanide will attack the slightly positive carbon, and the electrons between the carbon and the oxygen will go to the oxygen, which is slightly negative. So that is the first step. This gives this product. So the O now has O minus, not slightly negative, it's now an O minus. And I have a bond between the carbon and the cyanide. Now, what is going to happen is that the oxygen of the O minus, again, lone pair of electrons from that oxygen, attacks the hydrogen of the cyanide, and the electrons between the H and the C. N will go to the C, so I am regenerating the cyanide ion. So it gives the cyanide ion again plus the product. Please learn this mechanism. Justify the use of the term nucleophilic addition to describe the mechanism of this reaction. So this was the reaction, and we were saying this is, if he says what is the name and type of reaction, it's a nucleophilic addition reaction. Why nucleophilic and why addition? Please remember, we said nucleophiles are species that have lone pair of electrons, so they are electron-rich species, and they attack an electron-deficient carbon atom by donating an electron pair. Now, the cyanide is a nucleophile because the cyanide has lone pair of electrons that attack the slightly positive carbon on the carbonyl group. So this is a nucleophilic reaction. Addition, remember, any addition reaction means I have 2 compounds joined together to form only one product. So I have only one product. This is an addition reaction. Explain why the product of the reaction is not optically active even though it contains a chiral carbon atom. So it has a chiral carbon, but because in order to get the product, the cyanide can attack from both sides with equal chances. So I get both optical isomers, and that means it's a racemic mixture, and the racemic mixture will have no effect on the plane of plane polarized light. So the cyanide ion can attack the carbon atom from both sides, and this produces both optical isomers in equal amounts. And this is what we call a racemic mixture, so there is no effect on the plane of plane polarized light. Question 15 says a reaction vessel contained nitrogen monoxide and oxygen in a 2:1 molar ratio. The mixture was allowed to come to equilibrium, forming nitrogen dioxide. So we're having nitrogen monoxide reacting with oxygen to give nitrogen dioxide. The volume of the vessel was 15 decimeter cubed. That's the total volume. The reaction was carried out at constant temperature and at a pressure of 200,000 Pascal. At equilibrium, there was a total of this number of moles of gas, and the mass of oxygen alone was 7 grams. Calculate the number of moles of each substance at equilibrium. Okay, at equilibrium we had 7 grams of oxygen, so I can get the number of moles of oxygen at equilibrium. Mass over molecular mass, remember this is O2, so the MR is 32, and we get the number of moles of oxygen. Now, what is the number of moles of NO? At the top of the question, it says that nitrogen monoxide and oxygen are in a ratio of 2:1. So that means that the number of moles of NO is twice that of oxygen. So that is the number of moles of NO. What about NO2? Well, he said at equilibrium there was a total of 0.69625, and that means that the NO2 will be the rest of the 0.69625 minus the total of oxygen and NO. That gives the number of moles of NO2. Calculate the value of Kc. Okay, what do we know? We know that this is the equation, and we know that these are the number of moles, and we know that the total volume of the vessel was 15 decimeter cubed. Remember that Kc involves concentrations. Concentrations means number of moles over volume. So I want the concentration of NO2 to the power 2 over concentration of NO to the power 2 times concentration of O2 to the power 1. So we put these number of moles over the volume. So each of these number of moles is over the total volume, which is 15. And this gives a Kc of 0.5732. Units. K must have units. So if you calculate the units, remember this is how I calculate it. If I have NO2 to the power 2, that means mole to the, each concentration is mole per decimeter cubed. If I have it to the power 2, then it's mole to the power 2 over decimeter to the power 6. And cancelling whatever is the same up and down, then the overall units for this Kc is mole to the minus 1 decimeter cubed. Calculate the temperature of the reaction mixture at equilibrium. What do we know? We know that the volume is 15. The pressure is 15 decimeter cubed. Please note, it is 15 decimeter cubed. Pressure is 200,000, and the number of moles is what is given here. So we use PV equals nRT. That means T is PV over nR. What is P? The pressure in this equation has to be in Pascal. The question gives it to me in Pascal. But the volume has to be in what? Remember, the volume has to be in meter cubed. And if I have it in decimeter cubed, I multiply by 10 to the minus 3. Divide by 1,000 to make it into a meter cubed. Then N is the number of moles given, R is 8.31, and what we get is the temperature in Kelvin. Under a different set of conditions, the reaction was carried out to find the initial rate of the reaction. He gives me the values for experiment 1 and the rate equation. Now, first, give the reason why colorimetry can be used to monitor the rate of the reaction. Why is it that I can use colorimetry for this reaction? You should know that NO is a colorless gas, NO2 is a brown gas. So we're having differences in color, and I can use that to determine the rate of the reaction. So this is because the nitrogen dioxide gas is reddish-brown, while the reactants, both reactants, are colorless. So I can use that to measure the rate. Use the data to find the value of K. Okay, we already said this is the rate equation. It's given in the question. So I can get K. K is the rate over these other ones. Put in the values from experiment 1 and we get 13.008. And you can say 13.01. That's fine. Units, you put the units of each of these, and the units are already given in the table. So if you cancel those that are up and down, the unit for K here is decimeter to the power 6, mole to the -2, seconds to the -1. State why the reaction is unlikely to proceed in a single step. What was the rate equation? This is the rate equation. So the rate equation says that 2 particles of NO should collide with 1 particle of oxygen. That means I need 3 particles to collide in the same step. This is highly unlikely. Usually 2 particles collide. But to have 3 particles colliding at the same in the same step, that is unlikely. So this reaction most probably goes through more than 1 step. A student proposed this mechanism for the reaction. Justify whether or not this mechanism, first, is consistent with the overall equation and with the rate equation. So if you have these 2 steps, how do we deduce the overall equation? Remember, we put them, and whatever is on both sides of the arrow is cancelled. So the N2O2 is formed in the first step but used up in the second step. Whatever is left is the overall. So this is correct. So it does apply to the overall equation. But what about the rate equation? The rate equation includes only the species in the slow step. Now, in this mechanism, the slow step involves only the NO. So this cannot be the mechanism. In order to have this rate equation, I need to include the concentrations of NO and the concentration of O2. So actually, if it is this, then the second step should be the slow step. Then in that case, when the second step is the slow step, then we include the reactants of both the first and the second. So this is not agreeing with the rate equation. Question 16 says iron, lead, and zinc can be extracted using a blast furnace, but aluminium cannot. In a blast furnace, iron is extracted from iron 3 oxide at high temperature. Some standard enthalpy changes of formation and standard molar entropies are shown in the table. The main reaction occurring in the blast furnace to form iron is this. This reaction is feasible at all temperatures. Calculate the standard entropy change of the system. So we have this information in the table and we want standard entropy change of the system. How do we get standard entropy change of a reaction? Remember, the delta S of the system is the total of the delta S of products minus the total of the delta S of the reactants. So looking at that table, we have 2 times iron. Iron is 27.3 plus 3 times CO2. CO2 is 213.6 minus the reactants. So we have in the reactants, we have Fe2O3, which is 87.4, and 3 times the CO, which is 197.6, and the total is a positive value for the delta S system. And remember, this is in joules per degree per mole. Calculate the standard enthalpy change for this reaction. Again, from the table, we can do a Hess's cycle in which we have this equation, and this is in the table, it's given as delta H of formation. So we're starting from the elements and going up and using the values in the table. The delta H of the reaction from this Hess's law is the delta H2 minus delta H1. So we use these values and we get a delta H reaction of minus 25. This is in kilojoule per mole. Explain how your answer shows that this reaction is feasible at all temperatures. Remember, if the delta S is positive, then the reaction is feasible. So the delta S total is the delta S of the system plus the delta S of the surroundings. We calculated that the delta S of the system is this. So this is what we got from our calculation. And you should know that the delta S of the surroundings is minus delta H over T. We have the delta H, which is a negative value. So if the delta H is a negative value, then the delta S of the surroundings overall is positive, and that means the delta S total is positive, and that means the reaction is feasible at all temperatures. The main reduction reaction of aluminium oxide in a blast furnace is shown. Calculate the temperature at which this reaction becomes feasible. So, using the same information in the table, we have information about the aluminium and the iron. So we're going to use this to get the Hess's cycle to get delta H. So delta H of this reaction is the delta H2 minus delta H1. And looking at the values in the table, the delta H of aluminium times 2, which is 0 times 2, and the delta H for 3 CO2s and so on. This gives a value of plus 827 kilojoules. Then we need to get the delta S of the system. Again, the delta S of the system is the S of the products minus the S of the reactants. So this comes out, remember that the S comes out in joules. So we need to change it to kilojoules so that both of them have the same units. Now, how do I know when the temperature, which temperature is the reaction feasible at? This is feasible if the delta S total is 0. And we said the delta S total is delta S system plus delta S surroundings. And that means the reaction is feasible if the delta S total is 0, and that means the delta S system is equal to delta S surroundings. Now, what is delta S surroundings? Delta S of surroundings is minus delta H over T. So I can use that to get the temperature. So delta S of the surroundings, which is 827 over T, is equal to the delta S of the system, which we calculated 0.0537. And working through the equation, we get that the temperature at which this reaction becomes feasible is 15,400 K, 15,400 K. This is a very high temperature. Suggests why aluminium is not extracted from its oxide using a blast furnace. Remember, the blast furnace is the one we use to extract iron, but we cannot use it to extract aluminium because, as we found from the calculation, we need a temperature of 15,400 K, and that is too high to be achieved in a blast furnace. Question 17 says, this question is about 4 isomers with the molecular formula C4H8O2. These 4 isomers can be identified using 3 chemical tests. Each test gives a positive result for only one of them. All 3 tests give a negative result for the 4th one. So we're required to give the 3 chemical tests required, and for each test, identify the reagent, give the positive observation, and identify the functional group of the isomer that gives the positive result. So these are the 4 isomers. Which test do we want to start with? Let's start with the chemical test for acid. What is the chemical test for acid? For butanoic acid, well, we should add a carbonate, like sodium carbonate, with acid. It gives bubbles of gas that turn lime water milky. This is due to the carboxyl group in the butanoic acid. What about the 4-hydroxybutanal? This is an aldehyde. The test for aldehyde can either be Benedict's or Fehling's or Tollens. So you can say Tollens reagent and it should give a silver mirror with the aldehyde, or add Benedict's solution, heat in hot water bath. Only the 4-hydroxybutanal gives a brick red precipitate due to the presence of the CHO or the aldehyde group. What else can we do? We have the 3-hydroxybutanone. I can do the iodoform test, add iodine in aqueous sodium hydroxide. The 3-hydroxybutanone would give a yellow precipitate and antiseptic smell due to the presence of the CH3CO group at the beginning on the left. So this group would give positive with the iodoform test. And of course, the one that does not do any of these reactions is ethyl ethanoate. The ester does not do any of these reactions. The 4 isomers can also be distinguished using NMR spectroscopy. State why it is not possible to distinguish any of these isomers from the number of peaks in their carbon-13 NMR. So I cannot distinguish them using carbon-13 NMR. Why? Well, if you look at each of them, all of them have 4 different carbon environments, so all of them would give 4 peaks in the carbon-13 NMR. So I cannot use that to distinguish between. Now complete the table below to give the number of peaks in a low resolution proton NMR. That means how many proton environments do we have? So for butanoic acid, can you see this? We have 4 peaks that will be obtained for butanoic acid. What about for hydroxybutanal? We have all of these, so 5 different proton environments. With ethyl ethanoate, we have 3. With the 3-hydroxybutanone, we have 4 peaks for 4 different proton environments. One of the proton NMR spectra has a peak with a chemical shift greater than 10 ppm. Identify the isomer. If you look at the data booklet, you'll find that the one that has greater than 10 is the acid. So the butanoic acid has an H of the carboxyl group, or the OH of the carboxyl group. This would give a peak in the proton NMR higher than 10 ppm. The high-resolution proton NMR of one of the isomers contains a multiplet of 5 peaks. So one of them has a splitting of 5 peaks. So it's a quintet. Which of these would give a quintet in its proton NMR? Of course, you know that there is an n+1 rule. That means if it's a quintet, that means it has 4 protons on the neighboring carbon. So this one, 4-hydroxybutanal, the protons on the carbon in the middle have 2 hydrogens on the neighboring carbon from one side and 2 hydrogens on the neighboring carbon from the other side. So it has a total of 4 hydrogens on neighboring carbons. This will give a splitting of 5 peaks. Question 18. Pentanoic acid is a carboxylic acid with Ka of this value. A student was asked to titrate 25 centimeter cubed of 0.12 mole per decimeter cubed pentanoic acid with 0.1 mole per decimeter cubed potassium hydroxide. This is the equation. The teacher asked the student to sketch a graph showing the expected changes in pH as potassium hydroxide is added. So we have in the flask, we have the acid, pentanoic acid, and we're adding the base from a burette, and we are trying to determine where do we have expected pH changes. The student first identified 4 key points for the sketch graph using 4 calculations and 1 chemical equation. These are the 4 key points. At key point 1, before any potassium hydroxide has been added, the pH is 2.9. Use a calculation to justify this value. So what is the original pH that we're starting with? Looking at the information in the question, it says I have this Ka, this value for Ka, and we use 25 centimeter cubed of 0.12 mole per decimeter cubed pentanoic acid. So I can use this to get, this is a weak acid of course, and we said to get the concentration of H plus ions for a weak acid, it is this equation, square root of Ka times concentration. So the Ka I have, the concentration is 0.12 mole per decimeter cubed. So this is the concentration of H plus. How do we get pH from concentration of H plus? The pH is minus log concentration, and that means the pH is 2.9. The student deduced that the pH at key point 4 must be less than 13. So can you see key point 4? This is when we have added excess of the potassium hydroxide. Use a calculation to justify the student's deduction. You're not required to calculate the exact pH of the solution. So at key point 4, what is the pH? At key point 4, we already know that this is the concentration of potassium hydroxide. So that means the concentration of H plus times OH minus is 10 to the minus 14. I can use that value to get the concentration of H plus. So the concentration of H plus is 10 to the minus 13, and the pH is minus the log of that. So the pH comes about 13. So that means that the pH is around that at key point 4. The student deduced that the neutralization point of the graph at key point 3 would be 30 centimeter cubed. Use a calculation to justify the student's deduction. So we put key point 3 as the point of neutralization, and the student put it at 30. So the volume of KOH needed is 30. Looking at this equation, we said we added 25 centimeter cubed of 0.12 mole per decimeter cubed pentanoic acid. So the number of moles of acid is what? It's 0.003 mole. Concentration times the volume. Number of moles of the KOH from the equation would be the same. So I can get from that, I can get the volume of KOH needed. We already know the concentration of the potassium hydroxide. So divide number of moles by concentration. This gives 0.03 decimeter cubed or 30 centimeter cubed. So from the calculation, the neutralization points should happen after adding 30 centimeter cubed of the KOH. The student deduced that when equal amounts of pentanoic acid and potassium hydroxide had been added at pH 3, at key point 3, the pH would be greater than 7. So the key point 3, we've added equal amounts of pentanoic and potassium hydroxide, remember that the pentanoic is a weak acid. Potassium hydroxide is a strong base. If we titrate a weak acid with a strong base, the salts of the weak acid would have a pH higher than 7. The student deduced that at key point 2, can you see where key point 2 is? 15 centimeter cubed of potassium hydroxide would have been added and the pH would be 4.9. So key point 2 is halfway to the neutralization point, and halfway we know that the Ka is this value. At half the neutralization point, the concentration of the ion, pentanoate ion, would be equal to concentration of pentanoic acid. Remember that here we are in a buffer region, so the pH is equal to pKa plus the log of concentration of the pentanoate over concentration of the acid. Log of 1 is 0, and that means the pH is equal to pKa at half the neutralization point. The pKa is minus log of the Ka, so that means that the pH would be 4.9. The student then completed the sketch of the graph. So this is what the graph should look like, by linking these 4 points to show how the pH would change as the potassium hydroxide was added. Explain why the student drew the line so that the section of the graph between 5 and 25 centimeter cubed, the pH changes very little as we add potassium hydroxide. Again, remember that that part is the buffer region. So this region is a buffer region in which the acid is, I have a lot of acid and I'm adding some KOH, so a small amount of hydroxide ions is added. The solution is acting as a buffer because we have a lot of H plus ions, so as I add the OH minus, the ratio of the concentration of acid to conjugate base will change only very little. The student carried out the titration using methyl orange as an indicator. The experiment did not give a satisfactory color change at the neutralization point, and the student continued adding potassium hydroxide until 50 centimeter cubed had been added. So if I want to choose an indicator, I should not choose methyl orange, because if we look at the data booklet, the methyl orange will change color between 3.2 to 4.4 of pH, and that means it will change color too early before we reach the neutralization point. So if we look at methyl orange, you should know that in acid it is red. So if I put it on the pentanoic acid in the flask, I am starting red. So at key point 1 it is red. Then it will change to orange before the key point 2, and it will remain orange till pH 4.4. And all that we have not come near the equivalence point. So it has already changed to yellow before the equivalence point, and it remains yellow at key point 3 and 4. The student found a bottle labeled acid-base indicator solution in the store cupboard. The student, having checked with the teacher, used this as the indicator for the titration. The initial yellow solution turned green at the neutralization point. So just the identity of the indicator including a justification for the color observed at the neutralization point. Now, this was the graph that we had. And if we look at this, then I want something that would change color before pH 8 point something. So looking at the pH range, the most suitable one, according to what he's saying it will turn green. It's originally yellow and it will turn green at the neutralization point. So if we look at this, this would be the bromothymol blue. It will change within the range of 7 point something, and originally it is yellow. So before the neutralization point it's yellow, Now, at the end, it wants to be blue. It needs to be blue. So in the middle, there is blue with yellow. So it turns green in the middle. So what we're looking at is the bromothymol blue. It's yellow in acid, blue in base, and when it is mixed, yellow with blue, it becomes green at the neutralization point. And that was the end of this paper. I hope this was useful to you. Thank you for listening.